So my name's Craig Labovitz. I'm with Arbor Networks. And I'll be speaking, I'll try to get you to lunch quickly, but speaking for a few minutes about some data collection we've been doing. We call it, not very creatively, the Internet Traffic Project. And really it's a collaboration amongst some researchers and about 78 different ISPs now, where we're collecting near real-time data. Though the data today is about 67 of those ISPs and a 2-year period. So listening to Jay's presentation, the keynote yesterday, made me nostalgic for what, I know Bill's sitting there, in the good old days of the NSFNet. Being somewhat facetious, but really for a period of about a decade, we had really good data on what the internet looked like. ESNet was tracking data, and NSFNet was. There were weekly and monthly called ARTS reports on protocol port distribution. Every prefix that was added had a NAC or ACR. We really knew what the internet looked like and had a really good data set. All that changed, of course, with the end of the NSFNet and the rise of the commercial internet. And today, there are some really good data sets out there. AT&T continues to produce really great studies of their backbone, of their routing, of their IGP. Akamai, Google, similarly, have really good data sets. But all these data sets generally are about individual ISPs or individual sort of content CDNs. If you look to a macro view of what the internet looks like, what you end up looking at is either BGP data, and there's been an incredible amount of BGP studies over the last couple of years, or you end up reading analyst reports. And I had an interesting experience. Before I joined Arbor, I'd often read the analyst reports, even back earlier in my career, reading about the rise of ATM and the expected growth rate of ATM and the measurement numbers on ATM. And the interesting thing is you read Gartner reports and Forrester, you read Network World, you read all these different analysts, and they're all different. They all have different graphs. How can all these measurement-based, survey-based data sets be different? And then I had sort of an epiphany working for Arbor, where I ended up meeting with a lot of analysts. And I learned the secret behind analyst reports. The secret being analysts talk to vendors, and that's where they get their information. Not that you shouldn't trust vendors, but at the end of the day, it turns out that a lot of the really macro-level data about gross internet trends is a little dubious. And it's not just the analysts. I'll try to keep this short, but a quick story. Danny and I do an internet security survey every year. Folks have seen it? A few? At any rate, as one of the questions in the survey this year, we asked, what's the largest botnet ISPs had ever seen? And we got some really great data. We got, like 70 ISPs all responded with the size of the botnets. One responded 10,000, another responded 100,000, one responded 5 million. I mean, this was really interesting data. So as an exercise, we called up some of these ISPs and said, wow, 1 million, 100,000, this is great data. What measurement techniques did you use to get this data? And to a one, there would always be a pause, and it looked like a big botnet, but there was no data to back it up. So I will assert, at least not the researchers so much, but certainly analysts and other communities looking at macro trends, not a lot of data, and a lot of data actually being made up. So one of the things we've been working on over the last 2 years is really trying to leverage what's a growing internet-wide data collection infrastructure. To date, this coverage covers some 2,500, now today maybe closer to 3,000 active probes. The probes are across some 250 ISPs with a worldwide geographic footprint. And not only are the probes are generally collecting flow or DPI, but what's really interesting about the probes is they're in cool bits of the network. That is, they're not off T1s, they're generally not off OC3s, but generally they're collecting flow, net flow, C flow, J flow, whatever your variant is, from all the transit border routers of a given ISP or CDN or content provider. So really interesting bits of the network monitoring routers that have the OC192, OC48, et cetera links. Not enterprise, not customer networks, but really core bits of the infrastructure. And we're collecting a range of data sets, traffic, DPI, mitigation data, over a very large geographically, topologically diverse footprint. And, I think we've been talking about collaboration. There's been a couple speakers had mentioned collaboration, including the last one, between ISPs. Really, this is an outgrowth of an earlier effort Going back about 2 years, there was a lot of skepticism. Would ISPs share security information? Would they publicly state they were sharing security information? There was NSPsec, but a lot of skepticism about the degree to which competitive ISPs would actually cooperate. So Arbor did what we called the Fingerprint Initiative about 2005, and much actually to my amazement, about some 45 ISPs publicly agreed and then actively began to share information amongst themselves, with Arbor being a third party. And we've also similarly had success with the security survey. So the project I'm talking about today really is an outgrowth of that, where today we have some 78, during the course of the study, 67 ISPs, many in this room today, or quite a few, all agreeing to share data anonymously, basically every hour, 5-minute aggregates, and some have been doing this for the last 2 years. Basically a quick graphic of the geographic distribution. The data we're collecting now covers 17 countries, a little bit dominated by the US and Europe, and I'll speak about that a little bit later, but fairly broad geographic coverage, and I'll show the breakdowns of these ISPs in just a slide. So over the course of the study, where we've got lots of the graphs coming from in the next couple of slides, basically it's 67 ISPs over a period of 2 years, giving us near real-time information. Today there's closer to 80 or 85 actively participating. One of the things we do with the data collection, the anonymous data collection, is we still ask the ISPs to self-categorize themselves. And this is the general breakdown of what they classified themselves as. Basically 4 Tier 1, 15 Tier 2, number of US and Europe MSOs, content providers, and 1 research and education. The rest chose not to classify themselves, and the problem with anonymous data is generally that it's anonymous. So we don't have a lot of insight into what the classification of the other providers is. The hourly data collection now covers 1,200 routers, growing number of interfaces, and about 2 terabits per second of average interdomain traffic. Most of the deployments actually have significantly higher backbone traffic, but again, the data we're really looking at is data that's going through the peering, the transit edge, really interdomain, inter-ISP traffic alone, and not the overall aggregate customer or backbone traffic data sets to kind of have a normalized view of the internet. And again, we've been doing this for quite some time now as a research effort since 2006. Just a couple slides on what we're collecting and how we're collecting, and then I'll try to get into what I think the more interesting bits, the graphics, and talk about what we're seeing from the data set. So generally, again, we're monitoring the peering edge routers, the transit edge routers, the Junipers, the Ciscos and the like, getting NetFlow, JFlow. We do have a growing number of DPI deployments, which are doing both 10 gig and 1 gig port span or inline, where we're getting DPI data from those. But that's still a small percentage of at least the anonymous data set collection we have. And generally, this data is all coming up to commercial probes, generally sample data. We've got a bunch of work to make sure we're not double counting data, and we're verifying the data against SNMP on a per interface basis to make sure flow and SNMP at least agree. One last slide on the nitty-gritty of the data. Basically, we're getting 5-minute traffic samples every hour for the last 5 minutes throughout the hour. The traffic data is basically in and out to the networks, and it covers lots of things the old NSFnet reports used to cover. Ports, protocols, ASNs, applications, and other sorts of breakdowns. The other interesting data set we have within the anonymous data is the ISPs are also reporting all the traffic anomalies they saw during the last day. Where traffic anomalies really are defined via commercial algorithms, via being really statistical variance from expected norms, as well as anomalies being things that never make sense, like all SYN traffic, all port, fragments, other types of things characteristic of DDoS attacks. I should mention one of the really interesting problems in the research community is distinguishing anomalies from attacks. What is an anomaly? Is it really an attack? What's really a DDoS attack? How do you tell? And there's actually dozens and dozens of research papers that go into this and complicated algorithms. We actually chose a simpler technique. We choose to call something attack when an ISP decides to actually black hole it or mitigate it through TMS or Cisco guards, or when they actually annotate it as an attack. So again, we're breaking down some of the attacks based on actually other insight we have within the data collection to what did the ISP do about the attack, as well as some other data manipulation I won't go into today. As I mentioned before, the data also includes some self-categorization. Are you tier 1, tier 2, tier 3, etc. Very similar to the peering DB sort of data, as well as your geographic area. One last slide. I don't think this really reveals that much. Basically, the ISPs all have at least one box that's their leader or controller, sending up data to central servers that Arbor owns and manages over XML, SSL, and it's all anonymous. With that out of the way, I'll get into the interesting bits, which is what does the data show? So here we have data across the 67 providers going back 90 days. Again, this is an ongoing part-time research activity, so we don't have the full 2 years. But it's looking at what are the significant protocols across the 67 providers. And I think just a couple of points on this page. One is that we're still seeing diurnal patterns, which for truly global coverage we'd expect to be a little bit smoother. So we do think we still have geographical and time biases. The other interesting bit in the data is that, no surprise, TCP dominates the 67 providers, followed by UDP, followed by GRE and other sorts of business ICMP protocols. The only thing I found interesting in this as well is I keep attending meetings and hearing about the rise of IPv6. So we went looking at least for tunneled IPv6. We also have some V9 NetFlow deployments, which would give us the version. And it's I don't have the graph of just V6, but basically it's a line that's really, 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 really close to 0. So still waiting to see as IPv6 emerges, both tunneled and native. Certainly there may be a lot of native IPv6 that we're not seeing, and that might be the explanation as well. TCP port trends against the 60 providers. Again, going back 90 days. The data doesn't have too many surprises. TCP remains the dominant, followed by various file sharing protocols. I think the thing that was new to me is I hadn't realized over the last 2 years the rise of network news back from where last, I thought the network news model was dead and all the companies, the satellite companies and others had gone away and no one was interested in news anymore. I've since had an education both through this data set and talking to different ISPs that, peer-to-peer file sharing is, the availability of content, the quality of the content, the ease, accessibility of the content is nothing compared to what you can get from news today, without any of the annoying sort of throttling irritations of various DSL MSO providers. So we are seeing a fairly marked rise of network news over the last, certainly the last 2 years and certainly even over a 60-day period. And I hadn't looked at alt binaries in maybe a decade, and wow. I'll shift focus a little bit, talk about some of the attack data. Again, these are commercial deployments giving both statistical as well as, I don't want to call them fingerprints, but we call them misuse internally, evidence of SYN attacks, ICMP fragment attacks. Over the course of the study, there was about 600,000 anomalies, about 1,000 per day. Of these, again, we looked at the ones that we classified just as attacks. And once again, our algorithm for attacks are, did the ISP try to stop it? If the ISP tried to stop it, that pretty much counted as an attack to us, as well as looking at some of the misuse data. Just to give you a sense of the data, it's kind of interesting from our vantage point. I don't know if interesting is the right word, but to watch large-scale DDoS attacks go out across the internet. What you're looking at in this slide is a single day. Each color represents a different ISP. Again, there's 67 during the study ISPs participating, and each line represents an attack. What you're seeing in this slide is an outbound attack from 7 different ISPs, where the attack varies over SYN, flood, ICMP. And it's kind of cool. You can see the attack all start up at once. 7 different providers, the attack goes out. It's all going out against a single Russian AV vendor who seems to regularly incur the wrath of the internet's DOS attackers. But what is interesting is we really do have, again, not a micro vantage point, but suddenly we're starting to get a macro vantage point of watching basically our customers attack each other. And in this case, by the way, the Russian upstream was not a customer. They actually are now. But you do gain an interesting insight to watch the attacks propagate against the internet, across the internet in different ISPs as the day progresses. And this was actually a fairly reasonable attack. I think it was getting into the 7 million packets per second as the day progressed. Looking at a few other data sets, we looked at the packet size distribution, what were the common packet sizes used in the attack data. And not surprisingly, small packet sizes, basically 40 bytes, predominate. There are some interesting other, and I don't think we really have an answer yet for what the other spikes are. Our best guess is that these really represent fingerprints of other types of attack tools. Lots of attackers are using canned, Windows-based attack tools. Lots of botnets have some hard-coded sort of scripts. And we think that these might be fingerprints of some of those individual tools, as well as we're seeing a rise in application-level attacks, and attacks more focused on SQL level, web level, other sorts of levels. This slide is basically excluding floods. There continue to be a lot of floods, where floods I mean really trying to fill the pipe. We're trying to exhaust bandwidth in a bottleneck, upstream bandwidth, exhaust router, exhaust switch capacity. This slide is actually excluding the flood efforts and looking at, we call it internally misuse, but when there are, excluding the floods, looking at what the attack breakdown is. And, I don't know if it makes me optimistic or sad, but 9 years after the first, massive SYN floods against Microsoft and others, the majority of attacks out there still are, TCP SYN floods still continue to dominate. For most providers, it's relatively straightforward now to handle a lot of these TCP SYN attacks, but certainly not across the board, and certainly continues to be very prominent. ICMP attacks also continue to be prominent down below as well. We looked at what ports were actually being attacked, and as I mentioned, we're just really starting to see a rise in application-level attacks now. But when we look at the ports, web continues to be one of the most significant things attacked. Certainly in our local university environment, IRC servers are always popular. And fragmentation attacks continue to have fairly significant statistical indicators as well. One of the, I think, interesting things in this slide and next slide is really the growth of the size of attacks. As cable modem speeds have been increasing across the world, and consumer access, and you've got fiber to the home, bandwidth to these botnets has been growing correspondingly as well. Certainly going back a couple of years, a 500 meg attack going back 6-7 years was impressive. Even going back a year, we really hadn't seen many attacks over 20 gig. This slide's a little bit old, but we're now seeing, fairly common gigs over 10 gigs. And this slide is actually showing the number of attacks during the study period at 25, 24, all the way down to 1 gigabit. And we really are seeing an interesting growth in some of these, I still consider them, fairly large 25 gig, certainly 10 gig and above attacks, which continue to be, I think, even for large providers, tier ones, 25 gig is still, it's a little bit of bandwidth. It can be an issue to mitigate. Similarly, we're seeing growth in the other end of the spectrum in the 1 gig attacks. And for the 225 gig attacks, it actually all was within 1 day and within a 35-minute period. So some very sizable attacks out there. And the next graph, I think, gives sort of an indicator both to the number of attacks as well as to the size. This slide really shows between 2000 and 2006 year-to-year comparison. And what you'll see is the number of attacks and the size of the attacks in 2007 is dramatically larger than 2006. Probably not a surprise to most of the providers in the audience that the bandwidth, number of attacks, size of attacks is growing. The only thing I think I like, and I know Danny always brings this up when he presents these slides, and I think, I don't know, maybe it makes us feel better. It's nice to know that there's holiday seasonality to DOS attacks. Nice to know that even hackers and extortionists have families, take time off. But the holiday season, things always drop significantly in terms of the number of attacks and size of attacks. So maybe there's hope for all of us and the humanity in all of us. So trying to finish up with just a few minutes for questions. So my goal really was to give just a quick overview of some of the data we're trying to collect, certainly solicit feedback, and encourage participation. What we're really trying to do with this data today is, number one, this is really much more of a research effort, certainly within Arbor, my participation, than a commercial effort. So we're really trying to ramp this up a bit. And in doing this, it's kind of interesting to balance some of the business privacy issues, commercial interests within the research. We think this is really an important way to gain a global view, a macro view of internet traffic attack trends. We really are trying to grow the participation. At the same time, there's some very thorny business and legal and other issues that we're addressing with providers in sharing this data. It's also, one of the things we really want to do with the data set is, unlike some of the analyst reports, actually have a reasoned, methodology behind extrapolating the data and actually making statements about, from these 78, from these 100 providers, here is an estimate of overall internet traffic. And it turns out that's actually a hard problem. The self-categorization of the ISPs I showed before is a good example. Initially, we had one ISP based in Eastern Bloc who declared themselves a Tier 1. And I think they really meant is that they were the national PTT, but even asking folks to self-categorize themselves to try to use that to extrapolate from is problematic. And even when you deal with a Tier 1, it turns out with most Tier 1s, there's often 7 or 8 business units, wholesale, international, domestic, all with different infrastructure, different numbers. Very difficult to understand how to combine and extrapolate that data. Lastly, we really are continuing pursuing this as a research effort, and we do have a number of collaborations. Princeton University, I managed to get we have an intern funded this summer who will be working with us, as well as being able to share the data with other researchers. Now with that, I will open up for questions. Bill.
The first thought that I had when I saw your number of 357,000 attacks, is it easy or difficult to identify a discrete attack?
The definition of an attack is difficult in that, often these attacks include multiple vectors. There's a SYN flood, there's a ping flood application attack. They start at different times. So there's a lot of
But is it at one source, and that's a discrete, that counts as one?
The sources may change and the destinations may change. They're all within the same, insider usually, so they look like they're the same attack. But okay. There's, very imprecise definitions of what constitutes an attack.
Okay, and the last question was, with TCP resets, with that particular account, we've all heard about perhaps one MSO in particular shutting down peer-to-peer by sending TCP reset. So I'm wondering if that attack number includes attacks against one's own customers.
Yeah, the data does not include that, but there are some other interesting studies on that, on TCP resets. I think we have time for just one or two more questions. Sean?
Quick questions. Spoofing, I don't quite know how you could detect spoofing, but were you able to detect spoofing? And the second question is regional or national differences in either the sources, the targets, or the types of attacks.
Yeah, let me take the latter first. So there are actually a couple of slides we have that didn't make it into this deck on regional distribution of attacks. And if you see me privately, I can share that data with you. Spoofing actually is really interesting. We do have a couple of slides on spoofing where we looked at the source addresses and tried to do some determination. But it's really hard, given especially NetFlow, to determine spoofing. One of the things we're excited about is the ability from some of the DPI information to at least tie TTLs back to sources and have some estimate of do things make sense. We do know on what interface things come in, and we do know, we can compare that against the BGP routing tables, and we've got some indication, but it's a hard problem, and we have some numbers, but they're, it's
That's
a
why
work
you
in
got the
progress.
researchers up there.
Yeah, we
Researchers.
Yeah,
It's
it's
a good
hard.
research problem.
Okay.
Roy Rubachevsky, Ripon CC. Of course, if you plot IPv6 data against IPv4, it's not interesting. I wonder if you try to zoom in IPv6 to look for like certain patterns or maybe change of pattern in IPv6 traffic.
Yeah, I didn't hear the question. Change in what in IPv6?
In IPv6 patterns, well, the traffic patterns
Oh,
or
patterns,
the
okay.
volume.
Yeah, again, one of the problems is this is kind of a side research effort that we're just starting to internally get some funding for, so we haven't had a lot of time to look at the data. I was actually really interested to see if I could see ITF and NANOG hours within the data to see actually those patterns, but we haven't done a lot of microanalysis on the IPv6.
David Barak, AT&T. Have you found that the majority of the sources and destinations of the attacks are single hop connected away, or are you finding that there are a bunch of networks which are providing transit for the attacks? And was there any visible effect on those networks?
Yeah, we also have some data we've done on that, and there's a bunch of both. I don't have the slides for the breakdowns, but again, if you see us, you see me privately, I can share some of that. But there's an awful lot of folks both providing transit. It's basically, whoever has the eyeballs tends to be a good source, and, transit networks tend to be a good source of transit. Is one way the data breaks down. And of course, content providers make great victims. Okay, last question?
Okay, Warren Kamari, Google. So what guarantee do I have that you're going to keep the data anonymous?
So that there is some contractual language or some legal language that folks sign as they participate regarding the data. So you've got that, and you've got Danny and my, I don't know what my charming dispositions and to trust. But we do have some legal language, and that this has gone through our legal and other ISPs' legal is the real answer.
Okay.
Okay. Thank you very much, everyone.